So last time we just started talking about, well, we finished talking about force fields and electric fields. And now we're going to talk about kind of the same stuff in terms of energy. So a profile of fixed charges, a collection of fixed charges, do they provide a conservative force or a non-conservative force? What? 50%, yeah, conservative. And so the fact that it's a conservative force means, well, for one thing, that's the only reason that you can represent it as a force field. And it also means that conservative forces, you can define potential energy. So you can represent the forces produced by these fixed charges as potential energy. The same way like in physics 1 you do for gravity and you do for the forces that springs apply to objects. Okay, so now we're going to talk about the potential energy of a test charge in an electric field. And that the electric field is caused by a collection of fixed charges. And what we want to figure out is between any two locations, and I guess I'll write them as A and B. What we want to know is we want to figure out the change in potential energy in going like to the point B from the point A. Okay. And this is the notation we used a lot last semester. So this says the change in potential energy of the test charge going to the first subscript from the second subscript. Okay, so that refers to two locations. And the reason we want to figure this out is because that's our lead into talking about voltage. And voltage, you just know, from your experience that voltage is an important thing in electricity because that's how you talk about what size battery to use. That's how you talk about the electric field that's produced by wall outlets, right? So voltage is an important thing with electricity. Okay, so there are two ways to calculate the change in potential energy. The first one is if you know the potential energy function, if you know the function for potential energy at a point, then the change in potential energy in going to the point B from the point A is just, you just get that by subtracting the potential energy at B minus the potential energy at A. Okay. So like, for example, when we're talking about potential energy, that isn't just electricity. Potential energy is any conservative force. So this is how you could calculate a change in potential energy, like for gravity, okay? And I'll do an example like that just to show how that works. Or did we already do the one with gravity? I don't think I have to do that again. We did, okay. But so remember yeah, I think you're right. So, but remember, like from first semester, we know how to calculate the potential energy due to gravity of an object at a point. It's just equal to mgh. Remember that? And so you take mgh at B, subtract mgh at A, and that would give you the change in potential energy. So that you can calculate directly. But that only works if you know the function for the potential energy, and that's not always the case. There's one other way to approach it. So this works if you know that function for the potential energy. If you don't know that function, but you happen to have a constant force, then the work is equal to the dot product of the force vector times the displacement vector. You can do that with a vector components as fx dx plus fy dy. And then use the fact that the change in potential energy is equal to the negative work. And I showed that last time, I think, using gravity. That's what I did with gravity last time. Okay, so there's two ways to do it. How do you choose which one to do? Well, use this one if you happen to know the potential energy function. Use this one if the force in that force field happens to be constant at every point. And if you don't have either of those, then you can't do it. But the ones we're going to do are you're always going to have one of these two options. Okay. So let's first do a calculation where we know the potential energy. Okay, so for a fixed point charge, capital Q, we know the potential energy function. And so the potential energy at the point, some point A, is equal to the constant K, the same one that we used for Coulomb's law, times the fixed charge times the test charge, and then divided by the distance between the fixed charge and the point A. And A is the location of that test charge, lowercase q. So for example, what's the change in potential energy of a +2 Coulomb test charge in moving from 1.5 meters to 3 meters away from a minus 0.5 Coulomb fixed charge. So let me draw this problem. So we have a fixed charge of minus 0.5 coulombs, and we want to figure out what's the potential energy in a test charge going from this location to this location. So we can think of this as the point A, this is the point B. Okay, the test charge is going this way. This location is 1.5 meters. This distance is another 1.5 meters. Okay? And so the way we would calculate this, we want to calculate a change in potential energy. We have two options, right? One is if we know the potential energy function. One is if we have a constant force. Well, we have a potential energy function for this. Do we also have a constant force in this force field? Is the force constant at every point? Remember, for the fixed charge, Coulomb's law applies. And so the force varies as this thing moves, right? You have r squared on the bottom. And so as the test charge moves through here, the magnitude of that force is changing, right? So we don't have a constant force. So the only option we have in this case is to calculate the potential energy using the function and subtract. Okay, any questions about that? All right, so the potential energy at the point A is that constant K, 8.988 times 10 to the 9th, times the fixed charge of negative 0.5 times the test charge of 2 divided by the distance between them. And so you get a potential energy. Can someone plug that in? It's about 3.6 times 1 negative 0.9 times 10 to the negative 9 times 10 to the 10. Or no, about negative 6 times 10 to the 9. And what are the units? So you could do it by thinking through what all the units of these are, but that's the hard way, and this one has complicated units. But this is a potential energy, so it has to be in joules. We're using SI units, so it has to be joules. And now the potential energy at B is 8.988 times 10 to the 9 times negative 0.5 times 2 divided by the distance between, so that's 3. And so this time you get minus 3.0 times 10 to the 9 joules. And so the change in potential energy in going to B from A is equal to negative 3 times 10 to the 9 minus negative 6 times 10 to the 9. So you get an answer of positive 3 times 10 to the 9 joules. Okay, so this says that the potential energy increases as you go from here to here. Does anyone have intuition about what the potential energy should do? Does that seem right or does that seem backwards? The potential energy of this particle is increasing as you go from here to here. Well, okay, so we have a negative fixed charge, a positive test charge. So those are going to attract. So you can think of it like in terms of gravity, right? You can treat it like there's gravity pulling, it's not gravity, it's an electric charge thing, but you can think of it as like gravity is pulling this charge towards it. Does it make sense that if you fight against gravity and go the other direction, the potential energy goes up? That's what we're... So think about gravity, like the equivalent would be taking an object and going from here and lifting it higher. Does the potential energy go up or down? Up, because potential energy is mgh, okay? So one thing to notice about potential energy is let's say any conservative force tries to move objects to a lower potential energy. Okay, so gravity's trying to pull things down to h equals 0. It's trying to reduce the potential energy. The potential energy due to electrical forces, if the objects are opposite charges, it's trying to pull them together. If it's like charges, it's trying to push them apart. Okay. So that's always like an intuitive thing that you should kind of have in mind about potential energy as we talk about this stuff.
So if the particles, if negative and positive were together like two magnets,
yeah,
then that would be considered ground.
Yeah, right, exactly, yeah. Notice though that if you remember, like there was always this arbitrary thing with the height when we talked about gravitational potential energy. You could choose your h equals 0 to be wherever you wanted, as long as you kept it consistent through the problem. So, and because of that, so you would think like that ground position you're talking about would have potential energy equal to 0 or something. Depending on where you put your ground, it doesn't necessarily have to be 0. The way we've defined it here, if these two things were overlapping, you'd have an R equals 0. You'd have a finite value divided by 0, and so you'd have a potential energy calculation of negative infinity. So all it means is that's the lowest it can go. All right, so now let's do the other type. This was okay for charged parallel plates what do we know about charged parallel plates? I always draw them vertical, but nothing changes if you draw them horizontally or diagonally or anything. You always have forces from the force field pushing from one plate to the other, depending on what the sign of the test charge is. And there's one special thing about the forces between these parallel plates. Yeah, right. So all the force vectors are the same. What that means is, well, we don't have a way to calculate the potential energy function. But since those force vectors are constant, we can calculate work equal to the dot product of the force and the displacement vector. Okay, so let me do an example like that. So consider a test charge of positive 1 coulomb, and let's say that we have charged parallel plates where the electric field vector is equal to 1 Newton per coulomb in the x direction, 0 in the y direction. Okay, so all the E vectors look like this. And let's say that the particle goes from the point A to the point B, moving horizontally a distance of 3 meters. And we want to know what's the change in potential energy going to the point B from the point A. Okay, we don't have a potential energy function, so we have to calculate the work. So work is equal to the x component of the force vector times the x component of the displacement plus the y component of the force vector times the y component of the displacement. Anyone have a feel for what the displacement vector is here? Yep, and it's a vector, so what component is 3? It's in the x direction. One way you could do it is just assign these, like put a coordinates system somewhere and assign these points. So you could call this point 30, this point 00, you know, like if you put the coordinate system here. Then your displacement vector would be 30 minus 00. Your force vector is this. No, that's not your force vector. That's the electric field vector. So how do you get the force vector? Well, remember we have this equation that says the electric field vector is the force vector divided by the test charge. That's an equation I gave you last time. And so that says that the force vector is equal to the electric field vector times the test charge. So the force vector is our electric field vector of 1, 0 times the test charge of plus 1 coulomb. And so we get a force vector of 1, 0. What are the units of the force vector? What are the units of this force vector? It's a force vector. Newtons, yeah. So the force vector is 1, 0. The displacement vector is 3, 0. So the work then is 3 times 1 plus 0 times 0. And so you get 3. And what are the units of the work? Yes. And you could think of this as the work going to B from A, if you want to. And so now the change in potential energy in going to B from A is the negative of the work in going to B from A. And so it's equal to negative 3 joules. Any questions about that? Okay, so basically, there are only 2 times that we're going to have to calculate that change in potential energy. One is a fixed point charge. In that case, you use the potential energy function. The other one is the parallel plates. In that case, you have to calculate work and go that way. Okay. What would you do if you had a problem with like a fixed charge of 0.2 coulombs and another one here of minus 1 coulombs and another one here of 5 coulombs and then another one here of, you know, minus 3 coulombs, and you wanted to figure out the potential energy in going from A to B after crying. So how would you calculate that? Well, if you think of this as fixed charge 1, fixed charge 2, fixed charge 3, fixed charge 4, you'd calculate the potential energy at A as the potential at energy of A due to that fixed charge 1, plus the potential energy at A due to the fixed charge 2, plus the potential energy at A due to that fixed charge 3, plus the one at 4. Okay, so you'd have to do 4 potential energy calculations using that potential energy function. Then you'd calculate the potential energy at B, and then, you know, do the subtraction the same way. So you can do this with a bunch of particles. I don't think there are any practice problems where you have to do that, but that's the way it would build up. So, you know, the idea of like, what's the use of being able to calculate the potential energy just for a single fixed charge? Like, how commonly does that occur? Well, the benefit is you can build up a whole bunch of charges with this additive approach. Okay, let's take a dance break. Come on, everybody. Come along and without a roof, hey, hey, hey. Because you probably have only heard that song like 4 times today. Okay. It's on, like every time I get in the radio, it's on. I don't ever get in the radio. Every time I get in the car, it's on the radio. I like it, but come on. Okay, is everyone ready to go back to physics now? That was refreshing though, wasn't it? Okay, so now, the moment we've all been waiting for, voltage. Yeah. So voltage is to change in potential energy as the electric field vector is to the force vector. That might come up on the SATs. I don't. Oh, okay, shoot. I should have told you earlier. So what that means is just like the electric field vector was equal to the force vector divided by the test charge, the voltage in going to B from A is equal to the change in potential energy in going to B from A, divided by Q. Okay, so it's, in both cases, it's the thing that we're used to, you know, the thing that we did first semester, like this is the force divided by the test charge, and the other one is the change in potential energy, which we're used to, divided by the test charge. So what's the point of that? Why do we divide out the test charge? It's the same reason we did it with the force vector. Yeah, exactly. Yeah, we want some way to describe the fixed charges that we have without having to supply what our test charge is going to be, because we might not know what that's going to be. Essentially, like if batteries were labeled with change in potential energy, you know, the guy at the store would have to like ask you what your test charge is going to be and then write it, you know, write the potential energy on the battery. Like that would be a nuisance. And then if you wanted to use a new test charge, you'd have to bring the battery back for him to scribble it out and write the new one on. This way, no matter what the test charge is, the battery can be expressed with a single voltage, 9-volt battery, and the outlet can be described as a 120-volt outlet. So the benefit, again, is that you can describe an electric field without knowing what the test charge will be. For point fixed charges, you can define an electric potential, let's say at a point A, that's equal to the constant K times the fixed charge divided by R, where R is the distance from the fixed charge to the test charge at A. So this is electric potential. And then the voltage in going to B from A is equal to the electric potential at B minus electric potential at A. So these are electric potentials. This is called a potential difference, you know, because you're subtracting those potentials. Or voltage. Come along and okay, so that's what voltage is. So voltage is, voltage tells you something about the potential energy that an object gains or loses moving over some distance, moving from here to there, you know. Okay, so now I want to talk about, just for a second, remember that we have, so let's think back to electric fields for a second. First, think about a fixed point charge. So let's say that we have, let's say this is positive. Anyone remember what the electric field looks like? Yep, it's all going out. And what happens as you get farther away from the point? Smaller, yep. So the electric field looks like that. Still going in the same directions as you get farther away, it's just smaller. And what do the field lines look like? Remember what the field lines are? Those are the ones, they don't give any magnitude. So here you can see the magnitudes, but it gets pretty cluttered, you know, because like if you drew a million of these vectors, they'd be overlapping each other. Instead, people often represent this just by field lines, which don't show anything about the magnitude. They just show the direction. And the idea of these field lines is that at any point along the field line, if you draw a tangent to the field line, that's the direction of the vector at that point. Okay, so the black is the E vectors. The red is the field lines. And now, in terms of electric potential, and remember electric potential is just related to potential energy. If the forces are going this way, in order for the potential energy to change, you have to make a motion along that force, right? Like think about gravitational potential energy. Like how do you change gravitational potential energy? It doesn't change it at all to just move horizontally, right? Because H stays the same. In order to change the potential energy, you have to go parallel to the force, right? You have to go up or down. I mean, you could go diagonally, but you have some component that's parallel to the force. So it's the same thing with electric potential. For the electric potential to change, you have to go parallel to this force, which means if you're looking for curves that have the same electric potential the whole way around them, you have to go perpendicular to all of these lines. Okay, and so if you take the shapes that are perpendicular to the field lines at every point, and those are circles, you get these closed curves where as long as you stay on one of these curves, the electric potential is constant. And so those are called equipotential lines. You know, the potential is equal. So that means that the electric potential is constant on each one. There were two other types of fixed charge profiles that we talked about. One was, so for B, let's think about two opposite fixed point charges. So here's the positive one, here's the negative one. What direction do those electric field vectors go? They go from the positive to the negative, and then they start, actually I'm going to skip the vectors and just go straight to the field lines because this one gets really messy. Okay? And then for this one, it's a little trickier to figure out curves that are always perpendicular to these field lines, but it looks something like this. They're not circular, but the idea is at every point, I drew these badly because this obviously isn't perpendicular, but at every point, the red and the green should be perpendicular to each other. In lab next week, we'll get to look at this stuff. We have a computer program where you'll actually see what they really look like, see the real shapes. Yeah, question? Oh. You don't have to, like you won't have to draw these on tests or anything, but understanding those ideas I think is sort of helpful. I mean, just sort of having a basic understanding. And then the last type is So C is for the charged parallel plates. So if this is the positive one, and this is the negative one, what direction do the field lines go? Yep, they're all totally horizontal. They always go from the positive to the negative. And so what direction do the equipotential lines go? Yep, exactly. Okay, let me just describe a couple of kind of hand-wavy topics. So hand-wavy stuff. This is, we're not going to do any calculations with this, but I just want to explain a couple of electrical concepts. The first is conductors. Conductors are materials where electrons are free to move. And what that means is if a conductor, a conducting material, is put in an electric field, charges will move until basically they run out of conducting material, until they get to the edges and are stopped because they can't move anymore. So for example, if you had an electric field with field lines like this, and you put one end of like a copper wire here, and the other end, so let's call this A and this B. Say this is a copper wire. Copper is a good conductor. Then electric charge will travel from A to B. Another way of saying that same thing is there's a high electric potential here, a low electric potential here. Charges want to travel from high electric potential to low electric potential, and so that potential difference, or that voltage, is going to make charges travel from here to there. So that's what makes electric current flow. That's what makes charges move. Yeah.
Why are the field lines not in, wouldn't they be in the copper wires on the?
Yeah, well, that's a good question. So you can remember the thing with when we were talking about when we first started talking about potential energy, we did a problem where there's a skier at the top of this hill, right? And we calculated how fast he'd be going at the bottom. And it looks like, how could we figure this out? We don't know anything about the shape of the mountain. But one thing, a key thing about conservative forces is all the stuff that happens in between, that doesn't matter. The only thing that matters are the potential energies at the two ends. Okay, and so that's what's going on here too. We don't care about any of this stuff. That can be in the field or out of the field. We just know that there's a higher electric potential here, a lower one here, and so charges are going to do whatever they're free to do to get from here to there. Since this is a conductor, they'll find their way there.
Yeah, but if the vectors are going, they're going through the copper wire, right?
Yeah.
So wouldn't the field line go through?
Well, they don't have to. I mean, this could be outside a thick wall where whatever is causing this electric field isn't there in the presence of the wires. All the charges know is the promised land is over here, and they don't want to be here because the electric potential's too high here. Let's go to B, and they'll just find their way there. It doesn't matter about what's going on here, you know. Okay, the opposite of a conductor is an insulator. And insulators don't allow movement of electrons. So no matter what potential difference there is between two ends of an insulator, or between two parts of an insulator, no electric current will flow. So examples of insulators are rubber, styrofoam, and so if instead of being made out of copper wire, this was made out of styrofoam, no matter how strong this electric field was, you wouldn't get any motion through this of electrons. You wouldn't get any electric current. Okay, so insulators like rubber, electrical wires are copper in the middle or something that conducts well, surrounded by an insulator so that the electrons won't leave the wire to your hand or whatever. They'll just keep traveling along the copper because that's the only way they can move. Okay. Any questions about that? By the way, this is kind of an interesting thing. Water, in fact, is an insulator. Pure water is an insulator. Electricity can't travel in water at all. But if you put some charge-carrying particles in the water, it becomes a good insulator. And so in practice, any water you encounter has things in it, salts and different types of electrolytes that can carry electric charge. And that's why it's dangerous to, you know, you don't want to stand in a puddle that an electric wire is in or whatever. It's not really the water that's carrying it, it's the stuff in the water. But the stuff in the water can move around very easily. And so, so yeah, it's not the water itself. If you had totally pure water, you could, you know, stand around in puddles with electrical wires all you wanted. Okay, the next thing, hand wavy thing I want to talk about is this idea of induced charge. If you hold a charged object near an uncharged conducting material, conductor, the charged object causes the motion of charges in the conductor. So for example, if you have, you know, say this object is, it might have some negative charges in it, but say it's charged so it's mainly positive out here. There's a stray negative in there somewhere, but the overall effect is that this is positively charged. And you hold it up to a wall that has some ability to conduct charge. It's probably not a great conductor, but it can conduct a little bit. The wall, like inside the wall, the charges are perfectly well distributed. There's no dominant charge in the wall. But what happens here is, since this is positive, the negative charges are attracted to the outside of the wall. So they go this way. The positive charges all head this way because they're repelled by it. And so you end up, even though this isn't charged on its own, you end up with an attraction between these two things. An example of that is, you know, when you rub a balloon on your hair and then hold it up to the wall. That's like, why does it stick to the wall? I mean, that seems, you're charging the balloon, but why would the balloon stick to the wall? There's no reason to think that the wall has the opposite charge of the balloon, but that's induced charge. So the balloon in the spot that you rub on your hair gets extra electrons. You hold it up to the wall. The electrons in the wall head farther into the wall. That makes the part near you more positive. And then they attract and the balloon sticks to the wall.
So where is the charge?
Which charge? This one?
The negative charge.
In the wall? Every object has tons and tons of charges. I mean, well, every atom has a negative charge and positive charge, has negative charge and positive charges in it. So there's tons of charges. It's just the reason that you don't notice the charges in most things is because they're all lumped together, like the negative charges and positive charges are next to each other. But if you get the electrons to, a lot of the electrons to move away from their atoms, you end up with a region that has a net negative charge and a region that has a net positive charge. So these end up being attracted to each other. These? Well, in this example, they just go into the wall, so we don't see the effect of what they do, but you would get an extra positive charge somewhere in the wall as you're pulling the electrons away from these atoms. Well, here, I think this will help. This works better with a balloon, but watch this. Okay. Let's stop there and talk about capacitors next time. Anybody have any questions about any of that? All right. Yes?
In this wall example, initially are the positive and negative charges, they're all one lump sum, if you're saying.
Yeah.
So then when the positive charge comes in, it's attracting the negative, but pushing the other positive away. Is that
Well, what it's really doing is the only thing that can move are the negative charges, because electrons can move, but protons can't. So this is an okay way to think about it in terms of like what's happening with electric current. But really all that's happening is electrons, all these atoms are neutral. And little by little, the electrons from the atoms are getting pulled that way. And that's making this stuff that's lacking electrons now have a more positive charge. It's not really like positive charges are moving that way, but that's the effect of it. Any other questions? Okay.